Hey guys, welcome to my channel Euclid Mathematics, and here second video on Yemen test. In my previous video we learned Yemen test and the example which is from CSIR NET, and in my second video I'm going to solve second example. Here it is my second example from CSIR NET June 2019, example number second, 3 marks, okay, which asks for 3 marks. That means we have to figure it out which one of the option is correct. It is for 3 marks, that means only one option is correct, okay. And example it is given here, g1 of x, okay, sequence of function g1 of x is nx upon 1 plus n square x square, and x which belongs to closed 0 open infinite, okay. Then we have to figure it out which of the following option true, okay, as n tends to infinity. We have to check whether which one of the option is true, okay. In most of the case we have to eliminate options. We have to eliminate wrong options, okay. Sometimes we cannot say the right option, okay. So we're trying to eliminate wrong option, okay. So here our option first which given gn tends to 0 pointwise but not uniformly, okay. So we need to know what is meant by pointwise and what is meant by uniformly, okay. So here in uniformly convergent means we learn already the uniformly convergent by using Yemen test, okay. So pointwise convergent means we have to substitute that 0 and infinity limit, okay, limit as 0 and infinity to the g1 of x, okay. When that g1 of x gives finite value for 0 and infinity, then we say that g1 of x is a pointwise convergent, okay. Or one more thing, if the sequence of function is a uniformly convergent, then we know the standard result that uniformly convergent implies a pointwise convergent, okay. So we have to check uniformly convergent, automatically it gets the pointwise convergent, okay. But if it is not, it is a pointwise convergent, we cannot say it is uniformly convergent. This is a sufficient case, so use it very carefully. Now go for the next option, gn tends to 0, that means it is a uniformly convergent. We have to check whether it is uniformly convergent or not, okay. That uniformly, that means it goes to 0. Now third option, gnx tends to x from all x is a closed 0 open infinite, okay. And fourth option, gn of x is equal to x upon 1 plus x square, okay. So gnx tends to this one, all x from closed 0 open infinity, okay. So now let's get started our solution. So for checking pointwise convergent, we have to apply limit as n tends to infinity, limit as n tends to 0, because of the interval is given 0 to infinity, okay, to our gnx, okay. Gnx is nx upon 1 plus n square x square. Similarly apply pointwise convergent to n tends to 0 here also, both of them at the same time. So limit as n tends to infinity, limit as n tends to 0. So here to cancel that denominator n, we know that if n goes to infinity and it is at part of the denominator, we say that it goes to 0. So try to remove that numerator from here. So numerator as it is here. Now take n common from the denominator. So if n common from n, it left 1 by n, okay. So here I took here 1 of nx totally common, okay. So 1 upon nx remained here, and nx from n square x square it left nx, okay. So that nx get cancelled with that nx, okay. So apply limit n tends to infinity, 1 upon nx plus nx, okay. So 1 upon infinity means it is 0 here, okay. And again this term it get removed here. Now remaining term 1 upon nx, that means 1 upon infinity as n tends to infinity. So it gives a 0 value. That means 1 upon infinity, I got the 0 for first limit n tends to infinity, okay. So we have to check whether the end point of our interval gives finite values or not, okay. Now in my second option, apply limit n tends to 0 to gnx, okay, n tends to 0, here gnx 0 into x upon 1 plus 0 into x, okay. Direct substitute the value as n tends to 0, okay, because 1 is present here, so it cannot go to the infinity, okay. 0 upon 1 plus 0, okay. So we know that 0 upon 1 plus 0 means 0 upon something always remains 0, okay. Remember, always keep in mind that 1 upon infinity 0 and 0 upon any type of a number always 0, okay. So we observe here at the end point our sequence of function gnx gives a finite value and exists, okay. So if it is finite value and exists, that means we say that gnx is a pointwise convergent to 0, okay. And in our option C and D, it is given here it converges to x. In our option C, it is given gnx converges to x, or gnx converges to 1 upon 1 plus x square when x belongs to this interval close 0 infinity. But as we solved before, we got the gnx which converges to 0 for that closed interval 0 open infinity, okay. That means we say that option C and option D is wrong, okay. And we got the gnx is a pointwise convergent. So first part of the option A, gnx is a pointwise convergent, okay. So we got this one, gnx as a pointwise convergent. Now leftover it is here, we have to check whether gnx is a uniformly convergent or not a uniformly convergent, okay. Now it's only the one part remaining. So for solving this one, we have to apply famous test, okay, Yemen test for the uniformly convergent. So let's get started for Yemen test. So here Yemen test, we know that we find first of all g of x, okay, in Yemen test. for here g of x, and we know that the g of x it is given, and x is a closed interval 0 open infinity. Okay, remember these values are in modulus. Okay, so we need to be careful about that modulus because we want mn positive, okay, not a negative. That's why this modulus is given. Okay, now let's find out the gx. Gx has a limit n tends to infinity gn of x. Okay, so apply limit n tends to infinity to gn of x. Okay, so we do not have to apply that limit n tends to infinity directly because we need to cancel that en first, because we want some finite values. Okay, so en get cancelled with that en. Take en common from here, we get the value 0. Okay, so now we got the g of x is a 0 here. Now substitute gn of x and g of x here. So we get the supremum of x belongs to closed 0 open infinity. Okay, nx upon 1 plus n square x square, and g of x it is 0. Now proceed to the further step. So here we want the value for nx upon 1 plus n square x square. This is the value for mn. Okay, but we cannot decide here whether our function g of mn, okay, sequence of function mn is having some certain values. Okay, so we need to find it out. Okay, so consider that as a some variable. So I consider here y as a nx upon 1 plus n square x square. Okay, now find out its differentiation. Okay, so u by v result, apply the differentiation of u by v. Okay, so we know that the differentiation of u by v as a v into derivative of u, or u into derivative of u minus v into derivative of u upon v square. Okay, that means v into derivative of u minus u into derivative of u upon v square. Okay, this is the differentiation by quotient rule. Okay, so this one is easy. Okay, now put y dash is a 0, that means whole terms become 0. Okay, if this term is 0, that means take that denominator here, that means denominator it goes to multiplicand of a 0, so it becomes 0. Okay, so numerator it left n plus n cube x cube. Okay, so multiply n under bracket n plus n cube x cube. Okay, so x it is remaining here. Okay, x it is here. Okay, so we can add that x here. Okay, x it is remaining here. So I consider y it is here nx upon 1 plus n square x square. Okay, differentiate it by using quotient rule of a differentiation. Okay, so I hope so this one is easy. Okay, so quotient rule of a differentiation, it says that derivative of u by v is v into derivative of u minus u into derivative of v upon v square. Okay, so apply this one, put y dash is a 0, that means this term be getting 0, so that denominator is multiplicand of 0, so that one becomes 0. So leftover term it is here. Okay, so multiply n under bracket n plus n square x square. Okay, n under here n square, n plus n cube x square minus 2n cube. Okay, so 2n square into n, 2n cube, and x into x square. Okay, so n plus n cube x square minus 2n cube x square. Okay, so n cube x square minus 2n cube x square, that means only remain minus n cube x square plus n it is here, which is equal to 0. So we want the value for x, so just adjust some of the terms, we get the value for x square. Okay, which is 1 upon n square. Okay, so that means x which is equal to plus minus 1 by n. So we got the value for x. Okay, so we want the mn in the terms of n only. Okay, so put that x in the mn, so we get the mn in the terms of n only. Okay, so we can see here mn as a nx plus 1 plus n square x square, so x is a 1 by n. Okay, so here we got the value for x is a plus minus 1 by n. Okay, but we don't have to go for the negative because mn is in a modulus, so whether it goes to positive or negative it doesn't matter. Okay, so n it is here, n as it is here, and x is a 1 by n, 1 plus n square. Okay, x square is 1 upon n square. Okay, so n it here n square, so get this one get cancelled, 1 upon 1 plus 2. Okay, 1 plus 1 it get 1 by 2. Okay, so when we apply limit n tends to infinity to our mn, we got the value 1 by 2, which is a non-zero. Okay, so we know that if mn is a non-zero when apply limit n tends to infinity, then our sequence of a function not uniformly convergent. Okay, on that particular interval. Okay, so here close 0 open infinity. Okay, so we know that if sequence of a function it is pointwise convergent, that means it cannot guarantee as a uniformly convergent. Okay, or if it is uniformly convergent, we cannot guarantee for the we can guarantee for the pointwise convergent. Okay, if it is not uniformly convergent, we cannot say the pointwise convergent. Okay, so let's check out which one of the option is true from our question. So in our option number D, we already found that one is wrong. C also wrong. B is given Gn as a 0 uniformly convergent, but we got the Gn of x which is not uniformly convergent, so option B is wrong. Let's go for the option. It says that Gn pointwise convergent. Yes, we got the Gn pointwise convergent, but it is not uniformly convergent. That means our option number first is true. Okay, option A is true. So here is the solution of my second example from MN test. Okay, I hope so you found that MN test easier to understand. Okay, thank you everyone. Thank you for my today's lecture.